All right. So on Monday, we had kind of a longer lecture about core topics in exploration. In today's lecture, we're going to do something a little different. I'm actually going to discuss a different perspective on exploration, which is quite distinct from the one on Monday, and a little bit unusual. This is not how most people think about exploration problems, but I think it offers a different perspective that might get us thinking about what exploration really is. So this lecture is much more of kind of a state-of-the-art research-focused lecture, partly to get you thinking about final project topics, partly to just get you thinking about how else we could consider the exploration problem differently from how it is considered conventionally. And this lecture will be probably a little bit shorter and a little bit quicker to get through. All right, so what's the exploration problem? Just to recap from Monday. Well, the exploration problem can be kind of summarized with these two animations. So in homework 3, you used your Q-learning algorithm to learn a variety of Atari games, and probably some of them work pretty well. But some games are easy to learn, whereas others are seemingly impossible. And we learned on Monday how this is due in part to the fact that some of these games have highly delayed rewards, where intermediate reward signals don't really correlate with what you're supposed to be doing. So that's what Monday's lecture was about. And conventionally, we think about exploration as this problem where you have to trade off exploration, exploitation, and figure out some way to incentivize your RL agent to visit novel, unusual states, or states where it has a lot of information gain. But here's a different way we can think about the exploration problem. What if we don't just consider delayed rewards or sparse rewards, but we consider a setting where the rewards are absent altogether? What if we want to recover diverse behaviors without any reward signal at all? So you could imagine this from kind of a more of an AI or kind of scientific perspective. You could say, well, human children, for example, seem to be able to spend copious amounts of time playing with things in their environment. Presumably they're not acting randomly, and presumably they're getting something out of this. It's a energy-intensive activity both for them and their parents, so there must be a reason why this is something that people do. Probably there's something that is learned through play, through undirected exploration, and it's not just random. There's some notion of goals being set, some notion of goals being accomplished, and some presumably very useful body of knowledge that is distilled into the brain through this activity. So why might we want to learn without any reward function at all? Well, perhaps we could acquire a variety of different skills without any explicit reward supervision, create a repertoire of those skills, and then use them to accomplish new goals when those goals are given to us. Maybe we can use some sub-skills that we can use with perhaps a hierarchical reinforcement learning scheme. And perhaps we can explore the space of possible behaviors to build up a large data set, so a large buffer that can then be used to acquire other tasks. So this is a pretty different way of thinking about exploration. Conventionally, exploration is thought of as this problem where you just have to seek out the states that have reward. Here we're thinking about it instead as the problem of acquiring skills that could then be repurposed later. If you want a kind of a more practically minded example, you could imagine that you have a robot in your home, and you buy that robot, you put it in your kitchen, and then you turn it on, and the robot's job is to figure out what it can do in this environment that could potentially be useful, so that when you come home in the evening and you say, well, now I need you to do my dishes, whatever the robot practiced during this unsupervised phase, it can repurpose to very, very efficiently figure out how to clean your dishes. So if you can prepare for an unknown future goal, then when that goal is given to you, you can accomplish it quite quickly. All right, so in today's lecture, we're going to cover a few concepts that might help us start thinking about this problem. This is a big open area of research. There are no fixed, known, and perfect solutions, but perhaps some of the concepts I'll discuss might help you start thinking about how formal mathematical tools and reinforcement learning algorithms could be brought to bear on this kind of problem. So we'll discuss first some definitions and concepts from information theory, which many of you might already be familiar with, but getting a refresher on those will be important for everyone to be on the same page as we talk about the more sophisticated algorithms that come next. Then we'll discuss how we can learn without a reward function to figure out strategies for reaching goals. So we'll have an algorithm that proposes goals, attempts to reach them, and through that process acquires a deeper understanding of the world. Then we'll talk about a state distribution matching formulation of reinforcement learning, where we can match desired state distributions and in the process perform unsupervised exploration. We'll discuss whether coverage of valid states, whether basically breadth and novelty is a good exploration objective by itself and why it might be. And then we'll talk about how we can go beyond just covering states and actually covering the space of skills and what the distinction between those is. All right, but let's start with some definitions and concepts from information theory before we dive into the main technical portion of today's lecture. So first, some useful identities. As all of you probably know, we can use P of X to denote a distribution, and of course we'll see that a lot in today's lecture. We saw that a lot already. And you can think of a distribution as something that you fit to a bunch of points, and you get maybe a density in continuous space or a distribution in discrete space. H of P of X denotes entropy, and we've seen this before. Entropy is defined as the negative of the expected value of the log probability of X. And intuitively, entropy quantifies how broad a distribution is. So if you have a discrete variable x, then the uniform distribution has the largest entropy, whereas a distribution that is peaked on exactly one value and zero everywhere else has the lowest entropy. So intuitively, the entropy is kind of the width of this distribution. So that's stuff that hopefully all of you are already familiar with. Now, another concept which maybe not everyone is familiar with, but that will come up a lot in today's lecture, is mutual information. The mutual information between two variables x and y, which we write with a semicolon like this, because we could also have mutual information between groups of variables. So you could have mutual information between x together with z and y, in which case you would write I of x comma z semicolon y. This is defined as the KL divergence, and remember KL divergence is a measure of how different two distributions are. It's defined as the KL divergence between the joint distribution over x and y and the product of their marginals. So intuitively, if x and y are independent of each other, then their joint will just be their product of marginals, and this KL divergence will be zero. As x and y depend on each other more and more, their joint distribution will be more and more different from their product of marginals, in which case you'll see the KL divergence go up. Now, we can write the mutual information as the expected, just using the definition of KL divergence, as the expected value under the joint distribution over x and y of the log of the ratio of their joint and the product of marginals. Intuitively, you can think of it like this. If these green dots represent samples from our distribution, here, looking at this picture, you notice that there is a clear trend. The y values clearly depend on the x values. They're not fully determined by the x values, but there is definitely a trend in a relationship. Whereas here, the y values seemingly don't depend on the x values. So in the top picture, you have high mutual information. Essentially, if I tell you x, you can do a decent job of guessing y. At the bottom, you have low mutual information. If I tell you x, you will not do any better at guessing y than if I hadn't told you about it. Now, one important thing about mutual information is that it can be also written as a difference of two entropies. So you can write the mutual information as the entropy of y minus the entropy of y given x. And this just follows from a little bit of algebra. So you can basically start with the definition at the top, manipulate that equation a little bit, and you will end up with the equation at the bottom. But this way of writing mutual information also has a very appealing intuitive interpretation. You can think of mutual information as the reduction in the entropy of y that you get from observing x. This is essentially like that information gain calculation that we saw in the previous lecture on Monday. So mutual information tells you how informative x is about y, and because it's symmetric, it also tells you about how informative y is about x. All right, so let's tie this into RL a little bit. So the kind of information theoretic quantities that will be useful in our discussion in today's lecture will be the following. I'll use pi of s to denote the state marginal distribution of policy pi. In previous lectures, I also referred to this sometimes as p theta of s, same exact thing. When I write h of pi of s, this refers to the state marginal entropy of the policy pi. Now, this is kind of an interesting quantity because it quantifies the coverage that our policy gets. So if you have a very random policy that visits all possible states, you would expect that h of pi of s would be large. Here's an example of how mutual information can crop up in reinforcement learning. And I won't go into this in too much detail, but it's a fairly intuitive concept that's worth bringing up. So one very classic quantity that has been defined in reinforcement learning in terms of mutual information is something called empowerment. So a lot of this comes from work by Daniel Blany and colleagues. Empowerment is defined as the mutual information between the next state and the current action. There are a lot of variants of empowerment. It has also been defined as the mutual information between the next state and the current action, given the current state, as well as other variants. But let's think about the simple version. The mutual information between the next state and the current action. If we substituted in the entropy equations that we had on the previous slide, we know that we can also write this as the entropy of the next state minus the conditional entropy of the next state given the current action. Why is this called empowerment? Take a moment to consider that. Empowerment in English refers to how much power you have, how capable you are of achieving your desired end goals. What does this equation tell us about empowerment? Take a moment to think about it. Maybe write a comment in the comments section. So the way that we can think about this equation is it's saying that you would like the entropy of the next state to be large, which means that you would like there to be many possible next states, but you would like that entropy to be small, conditioned on your current action. So that means that if you know which action you took, it's easy to predict which state you landed in. That means you have a lot of control authority about the environment. It means you have a lot of ability to deterministically influence which state you'll be in. On the other hand, if you don't know the action, you want the state entropy to be large. So that means that you have a variety of actions available to you, and different actions will lead to very different states. And if you have both of these things, then what you should get is an agent that places themselves in a situation where they have many actions available to them that will all lead to very different states, but will do so in a reliable and controlled manner. So if you have a room, maybe you want to stand in the middle of that room because from there you can access all the parts of the room deterministically. If you had just one of these things, that wouldn't do the job. If you just had the entropy over the next state, now that's not really providing you with empowerment because there you want to put yourself in a situation where the future is very random. Maybe it's out of your control. If you just have the negative entropy of the next state given the current action, that's not quantifying the notion that you want many options available to you. So there you might put yourself in a very deterministic situation. Maybe you're sitting at the bottom of a well. The next state is extremely predictable, whether you know the action or not, which means that the next state, given the current action, is also extremely predictable. So that would minimize the second term, but wouldn't maximize the first term. But if you have both of these terms, then the only way to satisfy that objective is to put yourself in situations where you have many actions available that lead to many different future states, but you have a lot of control about which state you get by choosing your action. So that's why this quantity is referred to as empowerment. And the main reason I wanted to illustrate this, we're not going to go into detail about empowerment in today's lecture, but I wanted to illustrate this just to give you sort of a taste for how mutual information concepts can quantify useful notions in reinforcement learning. So this can be viewed as quantifying a notion of control authority in an information theoretic way.